Trillions of electrons are spinning around atomic nuclei in your body at speeds that approach a significant fraction of the speed of light. According to the laws of classical physics, these accelerating charged particles should be radiating electromagnetic energy continuously, losing speed and spiraling into the nucleus within a fraction of a second. Your atom should collapse. Your body should disintegrate. You should not exist. We thought we understood how electricity and magnetism work. We had Maxwell's equations, which perfectly described electromagnetic fields and predicted that any accelerating electric charge must radiate energy away as electromagnetic waves. We were completely right about the equations. They work flawlessly for radio antennas, power lines, and every piece of electrical technology we use. But we were completely wrong about atoms. Electrons orbit atomic nuclei for billions of years without losing any energy at all, in direct violation of everything classical physics told us should happen. Here's what makes this impossibility so disturbing. If electrons actually behaved according to classical electromagnetic theory, atoms would collapse in approximately 1/10 trillionth of a second. That's faster than light can travel across the width of a proton. Matter itself would be unstable on timescales so brief that chemistry, biology, and complex structures of any kind would be impossible. The universe would consist of nothing but collapsed atoms and radiation. The numbers reveal the scale of this paradox. A single electron orbiting a hydrogen nucleus should radiate away its entire kinetic energy in about 1010 seconds, according to classical calculations. During this time, it would complete roughly 10 million orbits before spiraling into the nucleus. But real electrons maintain their orbits for timescales longer than the age of the universe itself. Something is protecting them from the electromagnetic catastrophe that classical physics predicts. This protection comes from quantum mechanics, the most successful and counterintuitive theory in the history of science. Quantum mechanics reveals that electrons don't actually orbit nuclei like planets orbit the sun. Instead, they exist in wave-like probability clouds that surround the nucleus, occupying specific energy levels that cannot be changed by small amounts. An electron can only gain or lose energy by jumping between these discrete levels, and when it's sitting in its lowest energy level, there's nowhere lower for it to fall. But this quantum solution creates mysteries even more profound than the original problem. Why do electrons behave like waves when we're not looking at them, but like particles when we try to observe them? How can a particle exist in multiple places simultaneously until the moment we measure its position? Why are energy levels discrete rather than continuous? And perhaps most disturbing of all, what determines when an electron jumps between energy levels? And how does it traverse the space between levels without ever being detected in the forbidden zones? Tonight, we're going to explore the most fundamental paradox in atomic physics, a paradox that forced scientists to abandon their classical understanding of reality and embrace a quantum world where common sense breaks down completely. We will discover how the greatest minds of the 20th century struggled to understand why atoms do not collapse, leading to revelations that changed our understanding of matter, energy, space, and time. We'll journey from the classical physics of the 1800s, where electromagnetic theory made crystal clear predictions about atomic collapse, to the quantum revolution that saved matter from destruction but introduced mysteries that persist to this day. We'll explore how electrons can be both particles and waves, how they can tunnel through barriers that should be impenetrable, and how they can be entangled across vast distances in ways that Einstein called spooky action at a distance. But this isn't just about historical physics. We'll reveal how this quantum behavior enables the technologies that define modern life, from the lasers that power fiber optic communications to the transistors that make computers possible. We'll discover how understanding electron energy levels led to solar cells, LED lights, and medical imaging techniques that can see inside the human body. And we'll explore how the same quantum principles that prevent atomic collapse might enable revolutionary technologies like quantum computers and quantum teleportation. The implications stretch far beyond technology. If electrons don't actually orbit nuclei, if particles can exist in multiple states simultaneously, if the act of observation changes physical reality, then the universe operates according to principles that seem to violate logic itself. We're forced to confront uncomfortable questions about the nature of reality, the role of consciousness in physics, and whether the universe exists in a definite state when no one is observing it. Consider what this means for your existence. Every chemical bond in your body depends on electrons occupying specific quantum energy levels. Every enzyme that enables life operates through quantum mechanical processes, where electrons tunnel through energy barriers that would be impossible to cross in classical physics. Every photon of sunlight that powers the biosphere is absorbed and emitted through quantum transitions between electron energy levels. You are not just made of quantum mechanical components. You are a walking, thinking manifestation of quantum mechanics itself. Scientists call this the measurement problem, and it strikes at the heart of what physics can tell us about reality. When an electron transitions between energy levels, it seems to disappear from one level and instantaneously reappear at another level without ever being detected in between. This suggests either that electrons can truly teleport across space, or that our understanding of space and time at the atomic level is fundamentally incomplete. The quest to understand why electrons do and radiate energy away has led us to the most exotic frontiers of physics. We've discovered that empty space isn't actually empty, but filled with virtual particles that pop in and out of existence. We found that particles can influence each other instantaneously across arbitrary distances. We've learned that the future can influence the past under certain quantum conditions, and that information can be transmitted in ways that seem to violate the speed of light. If you are fascinated by the deepest mysteries of reality and want to understand how quantum mechanics prevents the collapse of matter itself, subscribe and hit the thumbs up button. And here is a question that will haunt you after watching this. If electrons can exist in multiple energy levels simultaneously until we observe them, what happens to all the unobserved quantum realities that collapse when we make a measurement? Comment below with your theory. I'll pin the most mind-bending response. The journey we're about to take will carry us from the practical reality of atomic stability that allows your existence to the theoretical boundaries where physics meets philosophy and science confronts its own limitations. We'll explore how the impossibility of radiating electrons reveals fundamental truths about the nature of reality, truths so strange that even the scientists who discovered them couldn't fully accept their implications. We'll discover that the quantum world doesn't just explain why electrons do and radiate energy away. It reveals that our entire classical understanding of particles, waves, energy, and matter is an approximation that breaks down at the scale where reality actually operates. The electrons that should collapse but don't are teaching us that the universe is far weirder, far more interconnected, and far more mysterious than human intuition could ever have imagined. Now, let us begin this journey into the quantum realm, where impossible things happen as a matter of course, where the act of observation creates reality, and where electrons refuse to follow the classical rules that should govern their behavior. Chapter 1. Classical Catastrophe in 1897. J. Thomson's discovery of the electron should have spelled doom for the universe. Not because electrons themselves were dangerous, but because their very existence created a paradox so severe that it predicted the immediate collapse of all matter. Thomson had identified particles 1,800 times lighter than hydrogen atoms, carrying negative electric charge, and somehow associated with every atom in existence. But when physicists tried to understand how these electrons could exist within atoms, they encountered what would become known as the greatest crisis in the history of physics. The problem was elegantly simple and devastatingly clear. By the 1890s, physicists had developed a nearly complete understanding of electromagnetic phenomena. Maxwell's equations described how electric and magnetic fields interacted with mathematical precision that bordered on perfection. These equations had predicted the existence of electromagnetic waves, leading directly to the discovery of radio waves and the development of wireless communication. They worked flawlessly for every electromagnetic phenomenon that could be tested in the laboratory. But Maxwell's equations contained an inescapable prediction that spelled disaster for atomic theory. Any electrically charged particle that undergoes acceleration must radiate electromagnetic energy. This wasn't a suggestion or approximation. It was a fundamental consequence of how electromagnetic fields behave in our universe. Accelerating charges create changing electric and magnetic fields, and changing electromagnetic fields propagate through space as waves, carrying energy away from their source. The implications for atomic structure were immediately catastrophic. If atoms contained electrons, and if electrons were held within atoms by attractive forces, then electrons must be constantly accelerating toward the positive charges in atomic nuclei. According to classical electromagnetic theory, this acceleration would cause continuous energy radiation. As electrons radiated energy away, they would lose kinetic energy, slow down, and spiral closer to the nucleus. The spiral would accelerate as the electron got closer, increasing the acceleration, and thus increasing the rate of energy radiation, creating a runaway collapse that would end with the electron crashing into the nucleus. The timescale for this collapse was shockingly brief. When physicists calculated how long it would take for an electron to radiate away all its orbital energy and crash into the nucleus, they found numbers that defied belief. A typical electron in a hydrogen atom would complete its death spiral in approximately 10 to 10 seconds, 1/10,000,000th of a second. That's roughly the time it takes light to travel 3 centimeters. Think about what this means. According to classical physics, every atom in your body should have collapsed before you could complete a single thought. Every atom in the Earth should have collapsed long before the planet could form. Every atom in the stars should have collapsed before nuclear fusion could begin. The universe should contain no stable matter of any kind, just radiation from the electromagnetic waves emitted during the universal atomic collapse, and perhaps some collapsed nuclei with electrons stuck to them in configurations that would make chemistry impossible. This wasn't a small discrepancy between theory and observation. This was a complete breakdown of classical physics in its attempt to explain the most basic fact about matter, that it exists in stable forms. The electron discovery had revealed that atoms must contain charged particles, but electromagnetic theory proved that configurations of charged particles could not be stable. Physics was caught in a logical contradiction that threatened the entire edifice of scientific understanding. The classical catastrophe deepened as physicists tried to find ways around the problem. Some proposed that electrons might not actually be accelerating within atoms, but this required abandoning the obvious fact that electrons must be held in place by some kind of force, and forces on charged particles inevitably produce acceleration. Others suggested that electromagnetic theory might not apply at atomic scales, but this violated the principle of universality that had made physics so successful, the idea that the same laws govern phenomena at all scales. One particularly desperate attempt involved proposing that atoms might be like tiny solar systems, with electrons orbiting nuclei in perfect circular paths, where the centripetal acceleration is exactly balanced by electromagnetic attraction. But this model faced an even worse version of the radiation problem. Circular motion is still accelerated motion, and accelerated charges still radiate electromagnetic energy according to Maxwell's equations. The planetary model of the atom simply created a more organized version of the same catastrophic collapse. The mathematical precision of classical electromagnetic theory made the problem even more frustrating. Physicists could calculate exactly how much energy an orbiting electron should radiate, exactly how its orbital radius should decrease over time, and exactly when it should crash into the nucleus. The calculations were straightforward applications of well-established principles that had been verified in countless experiments. Yet the predictions were spectacularly wrong. Atoms clearly did not collapse in fractions of seconds. This crisis revealed something profound about the nature of scientific progress. Physics in 1900 seemed nearly complete. Maxwell's electromagnetic theory unified electricity and magnetism. Newton's mechanics explained the motion of objects from projectiles to planets. Thermodynamics described heat and energy flow. The kinetic theory of gases connected microscopic atomic motion to macroscopic properties like temperature and pressure. Many physicists believed that only minor details remained to be worked out. But the electron radiation problem proved that this apparent completeness was an illusion. The classical physics that worked perfectly for large-scale phenomena failed completely at atomic scales. The universe was revealing that its fundamental operating principles were not just extensions of everyday experience scaled down to smaller sizes. Something entirely new and unexpected was happening at the atomic level. The classical catastrophe also highlighted the danger of extrapolating theories beyond their experimental domains. Maxwell's equations have been tested and verified for electromagnetic phenomena involving macroscopic objects, antennas, circuits, and laboratory apparatus. No one had ever tested whether these equations applied to individual electrons orbiting atomic nuclei, because no experimental techniques existed to probe atomic structure directly. Physics was making a logical, but ultimately incorrect assumption that laws validated, and one scale would automatically apply at all scales. As physicists struggled with the radiating electron problem, they began to realize that the crisis might be telling them something fundamental about the limits of classical thinking. Perhaps the problem wasn't that atoms were unstable, but that classical physics was incomplete. Perhaps reality at atomic scales operated according to principles that had no analogy in everyday experience. Perhaps the universe was about to teach humanity its first lesson in quantum mechanics. The classical catastrophe forced physicists to confront an uncomfortable truth. Their beautiful, mathematically elegant theories could make crystal-clear predictions that were completely wrong. This wasn't a failure of mathematics or logic. It was a failure of the basic assumptions about how nature works. The universe was about to reveal that it operates according to rules so strange and counterintuitive that even the scientists who discovered them would spend decades struggling to accept their implications. The electrons that should have radiated their energy away and collapsed into nuclei were somehow protected by principles that classical physics couldn't even imagine. The quest to understand this protection would lead to the most radical revision of our understanding of reality since the scientific revolution itself. Chapter 2: Quantum Revolution. On December 14, 1900, Max Planck stood before the German Physical Society and delivered a presentation that would shatter the classical understanding of reality. Desperate to solve a completely different problem about how hot objects radiate light, Planck had stumbled upon a mathematical trick that seemed to work but made no physical sense. Energy, he proposed, might not be continuous as everyone assumed. Instead, it might come in discrete packets, tiny, indivisible chunks that he called quanta. Planck himself didn't believe his own proposal. He thought of quantization as a mathematical convenience, a computational tool that would eventually be replaced by a proper classical explanation. But this mathematical trick contained the seed of a revolution that would completely transform our understanding of why electrons do and spiral into atomic nuclei. Energy quantization would prove to be not just a mathematical convenience, but a fundamental feature of reality itself. The revolutionary idea gained its first real support from an unexpected source. Albert Einstein's explanation of the photoelectric effect. When light strikes certain metals, it knocks electrons loose from their atoms. Classical physics predicted that brighter light should always knock out electrons with more energy, regardless of the light's color. But experiments showed something bizarre. The energy of ejected electrons depended only on the light's color, not its brightness. Dim violet light could knock out high-energy electrons, while bright red light couldn't knock out electrons at all. Einstein realized that Planck's quantum idea could explain this paradox. If light comes in discrete energy packets, photons, then each photon carries a specific amount of energy determined by its color. A single high-energy violet photon can knock out an electron, but many low-energy red photons cannot combine their energy to achieve the same effect. Energy transfer happens in quantum jumps, not gradual accumulation. This insight earned Einstein the Nobel Prize and provided the first concrete evidence that energy quantization was real, not just mathematical fiction. But the true quantum revolution began in 1913 when Niels Bohr applied quantization directly to the electron radiation problem. Bohr proposed something that seemed to violate basic physics. Electrons in atoms could only occupy specific discrete energy levels. Just as Planck had quantized the energy of light, Bohr quantized the energy of atomic electrons. An electron could exist in energy level 1, or energy level 2, or energy level 3, but never in between. The energy levels were like steps on a staircase. An electron could stand on any step, but could never hover between steps. This quantization solved the radiation catastrophe in one elegant stroke. If an electron sitting in the lowest energy level had nowhere lower to fall, it would stop radiating energy and remain stable indefinitely. The electron couldn't gradually spiral into the nucleus because gradual energy loss was forbidden. Energy changes could only happen in discrete quantum jumps between allowed levels. An electron in the ground state was trapped there by the granular nature of energy itself. Bohr's model was both brilliant and deeply mysterious. It explained the stability of atoms and successfully predicted the specific wavelengths of light that hydrogen atoms absorb and emit. When an electron jumps from a higher energy level to a lower one, it emits a photon with exactly the energy difference between the levels. When it absorbs a photon with exactly the right energy, it can jump to a higher level. This explained why atoms absorb and emit only specific colors of light, creating the characteristic spectral lines that had puzzled scientists for decades. But Bohr's model also raised profound questions that classical physics couldn't begin to answer. Why were only certain energy levels allowed? What prevented an electron from existing between levels? How did an electron know what energy levels were permitted before it even occupied them? And perhaps most mysteriously, how did an electron transition between levels? Did it gradually change energy, or did it somehow teleport instantaneously from one level to another? The quantum revolution deepened as physicists discovered that quantization wasn't limited to energy. Angular momentum, the rotational equivalent of linear momentum, was also quantized in atoms. Electrons couldn't orbit with arbitrary amounts of rotational motion. They were restricted to specific, discrete values. The universe seemed to be granular, not just in energy, but in fundamental physical properties that classical physics had assumed were continuous. This granularity extended to the very concept of motion itself. In classical physics, a particle has a definite position and velocity at every moment. But quantum mechanics revealed that electrons in atoms don't have classical trajectories at all. Instead of orbiting like planets, electrons exist in orbitals, three-dimensional wave patterns that describe where an electron is likely to be found if someone tries to measure its position. The electron isn't actually located at any specific point until the moment of measurement. The mathematical formalism of quantum mechanics, developed by Werner Heisenberg, Erwin Schrödinger, and Paul Dirac in the mid-1920s, provided precise tools for calculating atomic behavior. Schrödinger's wave equation could predict energy levels, chemical bonding, and spectral lines with extraordinary accuracy. But the physical meaning of the mathematics remained deeply mysterious. Schrödinger's equation describes electrons as wave functions, mathematical objects that contain information about probabilities, not definite properties. This probabilistic nature of quantum mechanics was perhaps its most radical departure from classical thinking. In classical physics, uncertainty about a particle's position or velocity reflects incomplete knowledge. If you had perfect information and unlimited computational power, you could predict exactly where every particle would be at any future time. But quantum mechanics suggests that uncertainty is fundamental to reality itself. An electron in an atom doesn't have a definite position that we simply don't know. It exists in a superposition of multiple possible positions until the moment someone measures it. The quantum revolution also revealed that the act of measurement plays a special role in physics. Before measurement, an electron exists in a quantum superposition of multiple energy levels simultaneously. The measurement process somehow collapses this superposition, forcing the electron to choose a specific energy level. This measurement problem remains one of the deepest mysteries in quantum mechanics. How does the smooth, continuous evolution of the wave function suddenly become the discrete, definite outcome of measurement? Bohr and his colleagues developed the Copenhagen interpretation of quantum mechanics to address these conceptual challenges. According to this interpretation, it's meaningless to ask what properties quantum systems have before measurement. Reality consists of measurement outcomes, not underlying properties that exist independent of observation. The wave function doesn't describe what's actually there. It describes what we can predict about measurement results. But not everyone accepted this radical revision of physical reality. Einstein famously objected that God does not play dice with the universe, arguing that quantum mechanics must be incomplete. He believed that hidden variables, properties we can't detect with current technology, must determine the apparently random outcomes of quantum measurements. Einstein spent decades trying to develop alternative theories that would restore determinism to physics. But experimental tests consistently supported the quantum mechanical predictions. The quantum revolution that began with Planck's desperate mathematical trick had completely transformed our understanding of atomic stability. Electrons don't radiate energy away because they're not actually orbiting nuclei in the classical sense. They exist in quantum states with discrete energies, trapped by the granular nature of reality itself. The smooth, continuous world of classical physics had been revealed as an approximation that breaks down at atomic scales. But the revolution also opened new mysteries that persist to this day. If quantum mechanics is correct, then reality at its most fundamental level operates according to principles that seem to violate common sense, logic, and even basic notions of causality. The quest to understand why electrons do and radiate energy away had led physics into a realm where particles can exist in multiple states simultaneously, where measurement creates reality rather than revealing it, and where the universe seems to be fundamentally probabilistic rather than deterministic. The classical catastrophe had been averted, but the price was accepting a quantum reality that no one, not even its discoverers, could fully comprehend. Chapter 3. Wave-Particle Mystery in 1924. A French graduate student named Louis de Broglie made a suggestion so outrageous that his thesis committee wasn't sure whether to award him a doctorate or recommend psychiatric evaluation. If light waves could sometimes behave like particles, as Einstein had shown with photons, then perhaps particles could sometimes behave like waves. Specifically, de Broglie proposed that electrons, the solid indivisible particles of matter, might actually be waves spread out in space. This wasn't just a wild guess. De Broglie had discovered a mathematical relationship that connected a particle's momentum to its wavelength, suggesting that every moving object in the universe has an associated wave. For large objects like baseballs and planets, this wavelength is so incredibly tiny that wave effects are completely undetectable. But for particles as small and light as electrons, the wavelength could be comparable to atomic dimensions, making wave behavior not just possible but dominant. The implications for atomic structure were staggering. If electrons are waves rather than particles, then the question of why they don't radiate energy away takes on a completely different character. Waves do an orbit. They exist as standing patterns that can maintain their shape indefinitely without losing energy. When you pluck a guitar string, the vibrating wave pattern persists until friction gradually damps it out. But in the vacuum around an atomic nucleus, there's no friction to damp electron waves. De Broglie's insight provided a revolutionary new way to understand Bohr's quantized energy levels. Instead of arbitrary restrictions imposed on electron orbits, these energy levels might represent the only wavelengths that can form stable standing wave patterns around a nucleus. Just as a guitar string can only vibrate at specific frequencies that fit exactly between its fixed ends, electron waves might only be able to exist at specific energies that fit exactly around the nuclear circumference. The mathematics was elegantly simple. For an electron wave to be stable, it had to complete an exact number of wavelengths as it wrapped around the nucleus. Half wavelengths or wavelengths that didn't close properly would interfere destructively with themselves and cancel out. Only electron waves with wavelengths that fit perfectly, one wavelength around the nucleus, 2 wavelengths, 3 wavelengths, and so on, could maintain stable existence. This wave model explained not just why energy levels were quantized, but why they had the specific values that Bohr had proposed. The allowed wavelengths translated directly into the allowed energies, and the resulting energy level predictions matched experimental observations with remarkable precision. The mysterious quantum restrictions that had seemed arbitrary in Bohr's model emerged naturally from the wave properties of electrons. But the wave-particle duality introduced mysteries even more profound than the ones it solved. How can something be both a wave and a particle? Waves are spread out through space, while particles are localized at specific points. Waves can interfere with each other and create patterns of constructive and destructive interference, while particles collide and bounce off each other like tiny billiard balls. These seem like fundamentally incompatible descriptions of reality. The mystery deepened when experimental tests began confirming de Broglie's predictions. In 1927, Clinton Davison and Lester Germer fired electron beams at crystal surfaces and observed interference patterns, the telltale signature of wave behavior. Electrons were somehow interfering with themselves, creating patterns of enhanced and diminished intensity that could only be explained if each electron was acting like a wave spread out over multiple paths simultaneously. Even more mysterious was what happened when experimenters tried to observe which path each electron took. When detectors were placed to monitor individual electron trajectories, the wave interference patterns disappeared, and the electrons began behaving like classical particles. The act of observation somehow changed the fundamental nature of electron behavior, transforming waves into particles through the simple act of trying to determine where they were. This observer effect struck at the heart of scientific objectivity. In classical physics, observation reveals properties that exist independent of the act of measurement. If you measure the position of a baseball, you're discovering where it already was, not creating its position through the act of measurement. But quantum mechanics suggests that electron properties don't exist in definite form until they're measured. Before observation, an electron exists in a superposition of multiple possible states, wave-like and particle-like simultaneously. The implications for atomic structure were profound. An electron in an atom exists as a three-dimensional standing wave pattern called an orbital. This wave pattern has no definite position. It represents a probability distribution describing where the electron might be found if someone tries to locate it. The electron doesn't orbit the nucleus like a planet orbits the sun. It exists as a cloud of probability that surrounds the nucleus in specific geometric patterns. These orbital patterns explain not just atomic stability, but the entire structure of chemistry. Different orbitals have different shapes, some spherical, some dumbbell-shaped, some more complex. The way these orbital shapes overlap and interact determines how atoms bond together to form molecules. The wave nature of electrons is responsible for every chemical reaction, every biological process, and every material property we observe in the world around us. But the wave-particle duality also revealed the fundamental limits of classical visualization. We evolved to understand a world of macroscopic objects that behave either like waves, water waves, or like particles, rocks, animals, planets. We have no intuitive framework for understanding objects that are simultaneously both waves and particles. Quantum mechanics forces us to abandon the classical assumption that microscopic objects are just smaller versions of macroscopic objects. The mystery becomes even more perplexing when we consider quantum superposition. Before measurement, an electron doesn't just have wave-like properties. It can exist in multiple energy levels simultaneously. The wave function that describes the electron contains components corresponding to different energy levels, each with its own probability amplitude. The electron is somehow in all of these energy levels at once until a measurement forces it to collapse into a single definite state. This superposition principle explains why electrons don't radiate energy away, even during transitions between energy levels. When an electron absorbs or emits a photon and changes energy levels, it doesn't gradually move from one level to another. Instead, the quantum superposition that initially contained components of multiple energy levels suddenly collapses into a superposition dominated by a single level. The transition happens instantaneously, without the electron ever existing in the forbidden zones between allowed energy levels. But instantaneous transitions raise their own puzzles. How can an electron change energy levels without spending time in intermediate states? How does it know which energy level to transition to when multiple transitions are possible? And how does the emission or absorption of a photon happen without violating conservation laws during the brief moment when the transition occurs? The wave-particle mystery has led to multiple interpretations of quantum mechanics, each offering different answers to these fundamental questions. The Copenhagen interpretation suggests that wave-particle duality reflects the limits of human knowledge rather than properties of reality itself. The many worlds interpretation proposes that all possible quantum states are equally real, existing in parallel universes that we can access. The pilot wave interpretation suggests that particles have definite positions but are guided by invisible quantum waves. None of these interpretations has achieved universal acceptance, and experiments designed to distinguish between them have so far failed to provide definitive answers. The wave-particle mystery that explains atomic stability has opened questions about the nature of reality that may remain forever beyond human comprehension. We know that electrons don't radiate energy away because they exist as stable wave patterns, but we still don't understand what it means for something to be both a wave and a particle simultaneously. The quest to understand why electrons don't spiral into nuclei has revealed that reality at its most fundamental level operates according to principles that transcend classical logic. The universe has taught us that our everyday intuitions about particles, waves, and the nature of existence itself are approximations that break down when we probe reality at its deepest levels. Chapter 4: forbidden zones between every pair of allowed electron energy levels in an atom lies something that defies classical understanding. A forbidden zone where electrons simply cannot exist. These aren't physical barriers that electrons bounce off, nor are they regions where electrons are destroyed or repelled. They are zones where the very concept of electron existence becomes meaningless according to quantum mechanics. The electron can be in energy level 2. It can be in energy level 3, but it cannot be in the energy levels 2.1, 2.5, or 2.9. These intermediate states are fundamentally forbidden by the granular nature of reality itself. This quantization of energy represents one of the most radical departures from classical physics in the entire quantum revolution. In classical mechanics, energy is continuous. A ball rolling down a hill can have any amount of kinetic energy between 0 and its maximum possible value. A planet can orbit its star at any distance corresponding to any energy level. But electrons in atoms are restricted to specific, discrete energy values with absolutely no possibility of existing in the gaps between them. The forbidden zones reveal themselves most dramatically in atomic spectroscopy, the study of light absorbed and emitted by atoms. When white light passes through a gas of hydrogen atoms, the emerging light shows dark absorption lines at very specific wavelengths. These dark lines represent photons that have been absorbed by electrons, jumping from lower to higher energy levels. But here's what's remarkable. The absorption lines are razor sharp, with no gradual absorption around the edges that you might expect if energy levels had some flexibility. This sharpness proves that energy levels are perfectly defined, with absolutely no tolerance for variation. An electron can absorb a photon with exactly the right energy to jump from level 1 to level 2, but it cannot absorb a photon with 99% or 101% of that energy. Photons with even slightly wrong energies pass through the atom as if it weren't there. The forbidden zones are so absolutely forbidden that they're invisible to electromagnetic radiation. The existence of forbidden zones creates paradoxes that classical physics cannot resolve. When an electron transitions from a higher energy level to a lower one, it must somehow traverse the forbidden zones between them. But if these zones are truly forbidden, how does the electron travel through them? Quantum mechanics suggests that the electron doesn't travel through the forbidden zones at all. It simply disappears from the higher level and instantaneously reappears at the lower level, releasing a photon with energy exactly equal to the difference between the levels. This instantaneous transition seems to violate basic principles of continuity and causality that govern classical physics. In the classical world, objects move continuously through space, occupying every intermediate position during their journey. But electrons transitioning between energy levels appear to teleport across forbidden zones without ever being detected in intermediate states. They achieve this apparent teleportation not by moving faster than light, but by following quantum mechanical principles that have no analog in everyday experience. The forbidden zones also reveal the profound connection between energy quantization and atomic stability. In classical physics, an electron spiraling into the nucleus would pass through a continuous range of energy levels, radiating electromagnetic energy at every point along its trajectory. But quantum mechanics restricts electrons to discrete energy levels with forbidden zones between them. An electron sitting in the lowest allowed energy level cannot radiate energy because there is no lower energy level for it to transition to. The forbidden zones below the ground state protect the electron from the classical electromagnetic catastrophe. But why do forbidden zones exist at all? The answer lies in the wave nature of electrons and the mathematical constraints of wave interference. Electron waves in atoms must satisfy specific boundary conditions. They must form standing wave patterns that don't change shape over time. Only certain wavelengths can create stable standing waves around the nucleus, and these allowed wavelengths correspond directly to the allowed energy levels. Think of the forbidden zones as wavelengths that cannot form stable patterns. just as a guitar string cannot vibrate at arbitrary frequencies, only at specific frequencies that fit exactly between its fixed ends. Electron waves cannot exist at arbitrary energies in atomic systems. The forbidden zones represent wavelengths that would create unstable wave patterns, causing destructive interference that would eliminate the wave entirely. This wave mechanical explanation reveals why forbidden zones are so absolutely forbidden. They are not prohibited by external forces or physical barriers. They are prohibited by the mathematics of wave interference itself. An electron trying to exist in a forbidden zone would be like a guitar string trying to vibrate at a frequency that doesn't fit its length. The wave pattern would immediately cancel itself out through destructive interference, making stable existence impossible. The sharpness of energy level boundaries reflects the precision of wave interference effects. When waves interfere constructively, they create stable patterns that can persist indefinitely. When they interfere destructively, they cancel completely with no intermediate possibilities. There are no partially interfering wave patterns. Interference is either constructive, destructive, or neutral. This binary nature of wave interference translates directly into the sharp boundaries between allowed and forbidden energy zones. Forbidden zones also explain one of the most important features of atomic behavior: selective absorption and emission of electromagnetic radiation. Atoms can only absorb photons with energies exactly matching the energy gaps between allowed levels. This selectivity is what creates the unique spectral signatures that allow astronomers to identify chemical elements in distant stars and galaxies. Each element has its own characteristic pattern of forbidden zones, creating a unique fingerprint in the spectrum of absorbed and emitted light. The medical technologies that save lives every day depend on the existence of forbidden zones. X-ray imaging works because different tissues have different patterns of forbidden zones, causing them to absorb X-rays differently. MRI machines manipulate the forbidden zones of hydrogen nuclei in water molecules to create detailed images of soft tissues. Laser surgery uses the sharp energy level boundaries to deliver precise amounts of energy to specific types of cells without affecting surrounding tissue. But forbidden zones also raise profound questions about the nature of reality and the role of mathematics in physics. The zones are forbidden not by physical laws in the classical sense, but by mathematical constraints that seem to have ontological reality. They actually determine what can and cannot exist in the universe. This suggests that mathematics might not just describe reality, but actually constitute reality at its most fundamental level. The absoluteness of forbidden zones also challenges our understanding of the relationship between the possible and the actual. In classical physics, anything that doesn't violate conservation laws or fundamental principles is potentially possible. But quantum mechanics introduces mathematical constraints that absolutely prohibit certain configurations, regardless of available energy or time. Forbidden zones exist not because they're dynamically unstable or energetically unfavorable, but because they're mathematically impossible. This mathematical impossibility extends beyond individual atoms to the collective behavior of matter. When many atoms interact, their individual forbidden zones combine to create forbidden zones for the entire system. This is why certain materials are insulators. They have large forbidden zones that prevent electrons from moving freely through the material. Other materials are conductors because their forbidden zones are small or absent, allowing electrons to move with relative freedom. The forbidden zones that protect atomic stability represent one of the most profound discoveries in the history of science. They reveal that reality is not just granular in its energy content, but absolutely discrete in its possibilities. The universe doesn't just prefer certain configurations over others. It absolutely prohibits vast categories of potential existence through mathematical constraints that operate at the deepest level of physical law. These zones that electrons cannot enter have saved matter from classical electromagnetic catastrophe, but they also open questions about the nature of existence itself that continue to puzzle physicists and philosophers today. Chapter 5. Uncertainty Principle. In 1927, Werner Heisenberg made a discovery that would forever change our understanding of what it means to know something about the physical world. While developing the mathematical formalism of quantum mechanics, he stumbled upon a fundamental limit to human knowledge, not just a practical limitation imposed by crude instruments, but a theoretical boundary built into the structure of reality itself. The uncertainty principle revealed that nature actively prevents us from simultaneously knowing both the position and velocity of any particle with perfect precision. This wasn't just bad news for experimentalists hoping to make more accurate measurements. Heisenberg's uncertainty principle provided the final piece of the puzzle explaining why electrons don't radiate energy away and spiral into atomic nuclei. The principle revealed that perfect knowledge of an electron's orbit is not just difficult to obtain, it is fundamentally impossible. And this impossibility of knowledge is precisely what saves atoms from collapse. To understand how uncertainty protects atomic stability, imagine trying to pin down exactly where an electron is located within an atom and exactly how fast it is moving. Classical physics assumed this information exists and could, in principle, be measured. But Heisenberg showed that the very act of measuring an electron's position necessarily disturbs its velocity, and measuring its velocity necessarily disturbs its position. The more precisely you try to determine one property, the more uncertain the other becomes. The mathematics of the uncertainty principle are elegantly simple but conceptually devastating. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than a tiny number called Planck's constant divided by 4. This might seem like a small restriction, but for particles as light as electrons, it means that precise knowledge of position and motion is fundamentally impossible, not just practically difficult. This fundamental uncertainty is what prevents electrons from following classical orbits. In classical physics, an orbiting electron would have a definite position and velocity at every moment, allowing it to radiate electromagnetic energy according to Maxwell's equations. But if electrons cannot have definite position and velocity simultaneously, then the entire concept of a classical orbit becomes meaningless. You cannot predict when and where an electron will radiate energy if you cannot know where it is or how it is moving. The uncertainty principle transforms our understanding of atomic structure from classical orbits to quantum orbitals, three-dimensional probability distributions that describe where an electron is likely to be found. These orbitals represent the maximum amount of information that can be known about an electron's location and motion without violating Heisenberg's principle. They are not paths that electrons follow, but regions where electrons might be detected if someone tries to measure their position. But the uncertainty principle implies something even more radical than imprecise measurement. It suggests that electrons don't have definite position and velocity properties before measurement. The uncertainty is not in our knowledge, but in reality itself. Before measurement, an electron exists in a quantum superposition of multiple possible positions and velocities simultaneously. The act of measurement doesn't reveal pre-existing properties, but actually creates them by forcing the electron to choose specific values. This creation of properties through measurement explains why electrons in atoms don't radiate energy continuously. An electron in the ground state of an atom exists in a quantum superposition where its position is spread out over the entire orbital and its velocity is correspondingly uncertain. Since the electron doesn't have definite position and velocity, it cannot undergo the definite acceleration that classical electromagnetic theory requires for radiation. The uncertainty principle protects electrons from radiating energy by preventing them from having the definite properties necessary for classical radiation. The principle also explains why atomic energy levels are discrete rather than continuous. If an electron could have any energy value, as classical physics suggests, then it would violate the uncertainty principle by having definite position and momentum simultaneously. Only specific energy values allow electron wave functions to satisfy both the constraints of atomic confinement and the requirements of the uncertainty principle. The allowed energy levels represent the only configurations where electrons can exist without violating fundamental limits on knowledge and measurement. Heisenberg's insight revealed that the classical concept of trajectory, the idea that particles follow definite paths through space and time, breaks down at quantum scales. Electrons in atoms don't follow orbits because orbits require definite position and velocity at every moment, which the uncertainty principle prohibits. Instead, electrons exist as probability waves that evolve according to Schrodinger's equation, never requiring definite classical properties. But the uncertainty principle creates its own mysteries. If electrons don't have definite properties before measurement, what determines the outcome when measurements are made? Why does an electron choose to appear at one location rather than another when its wave function contains multiple possibilities? And how does the measurement process transform the smooth, deterministic evolution of the wave function into the discrete, apparently random outcomes that experiments observe? These questions probe the deepest mysteries of quantum mechanics, the measurement problem that continues to puzzle physicists nearly a century after Heisenberg's discovery. The uncertainty principle tells us that perfect knowledge is impossible, but it doesn't explain how partial knowledge emerges from the fundamental uncertainty that characterizes quantum systems before measurement. The principle also has profound implications for the nature of causality and determinism. In classical physics, perfect knowledge of a system's current state allows perfect prediction of its future behavior. But if perfect knowledge is fundamentally impossible, as the uncertainty principle suggests, then perfect prediction is also impossible. The universe might be deterministic at the level of wave function evolution, but it appears random at the level of measurement outcomes that we can actually observe. This randomness is not just apparent but fundamental. Unlike classical randomness, which reflects incomplete knowledge of complex deterministic systems, quantum randomness appears to be built into the structure of reality itself. When an electron transitions between energy levels, the timing and direction of the transition cannot be predicted with certainty, even with complete knowledge of the quantum system. The uncertainty principle protects atoms from classical collapse, but does so by introducing genuine randomness into the foundations of physics. The technological implications of the uncertainty principle extend far beyond atomic physics. Every electronic device depends on quantum mechanical effects where the uncertainty principle plays a crucial role. Transistors work because electrons can tunnel through barriers that should be impenetrable according to classical physics, a process that is only possible because the uncertainty principle allows particles to borrow energy for brief moments. Laser technology depends on precise control of energy level transitions that are governed by the interplay between uncertainty and measurement. Modern quantum technologies push the uncertainty principle to its limits. Quantum computers use superposition states that exist only because the uncertainty principle prevents quantum systems from having definite classical properties before measurement. Quantum cryptography exploits the principle's measurement disturbance to detect eavesdropping. Any attempt to intercept quantum information necessarily introduces uncertainty that reveals the presence of unauthorized observers. But perhaps the most profound implication of the uncertainty principle is what it reveals about the relationship between knowledge and reality. Classical physics assumed that the universe exists in definite states independent of observation, and that measurement simply reveals pre-existing properties. The uncertainty principle suggests that this assumption is fundamentally wrong. Reality at quantum scales is indefinite until measurement forces it to become definite, and the limits on measurement impose limits on the definiteness of reality itself. The uncertainty that protects electrons from radiating energy away represents a fundamental feature of how information and reality interact at the deepest levels of physics. We exist because nature actively prevents the kind of precise knowledge that would allow classical electromagnetic collapse. But this protection comes at the cost of accepting a universe where fundamental randomness and measurement-dependent reality replace the classical ideals of determinism and objective existence. The uncertainty principle has revealed that the quantum mechanical solution to atomic stability is not just a different theory about the same classical reality. It is a quantum mechanical solution to atomic stability is not just a different theory about the same classical reality. It's not just a different theory about the same classical reality. It's not just ability, it's not just a quality, but necessarily atomic same classical reality. It's a completely different conception of what reality means at its most fundamental level. Chapter 6. Quantum Tunneling. Imagine walking up to a solid brick wall, casually strolling through it without breaking any bricks, and emerging unharmed on the other side. In the classical world, this is impossible. Particles cannot pass through energy barriers higher than their available kinetic energy. But in the quantum realm, this impossible phenomenon happens billions of times per second in every atom in your body. It's called quantum tunneling, and it represents one of the most counterintuitive consequences of wave-particle duality and the uncertainty principle. Quantum tunneling is directly related to why electrons don't radiate energy away in atoms. But it reveals this protection through an even more mysterious mechanism than energy-level quantization. Tunneling shows that electrons can violate classical physics not just by occupying discrete energy levels, but by moving through regions where they classically shouldn't be able to exist at all. This impossible motion is what allows complex chemistry, nuclear physics, and ultimately life itself to exist. To understand how tunneling works, consider an electron approaching an energy barrier, a region where the potential energy is higher than the electron's kinetic energy. Classical physics gives a clear prediction. The electron will slow down as it approaches the barrier stop when its kinetic energy equals the barrier height, and then reverse. Direction like a ball rolling up a hill and falling back down. The electron simply doesn't have enough energy to climb over the barrier. But quantum mechanics tells a radically different story. Because electrons are waves as well as particles, they don't interact with barriers in the same way classical particles do. When an electron wave encounters a barrier, part of the wave is reflected back, but part of it penetrates into the barrier region and potentially emerges on the other side. The electron has a quantum mechanical probability of tunneling through the barrier, even though it lacks the classical energy to go over it. This tunneling probability depends on the barrier's width and height in ways that classical physics cannot explain. Thin barriers allow more tunneling than thick barriers, and low barriers allow more tunneling than high barriers. But even insurmountably high barriers have some tunneling probability. There's always a chance, however small, that a particle will appear on the far side of any barrier through pure quantum mechanical effects. The mathematics of tunneling emerge naturally from Schrodinger's wave equation. The electron wave function doesn't stop abruptly at barrier boundaries, but penetrates into classically forbidden regions with exponentially decreasing amplitude. If the barrier is thin enough, some wave amplitude remains when the wave reaches the far side, allowing the electron to tunnel completely through. The electron never exists inside the barrier in a classical sense, but its quantum wave function connects the two classically allowed regions on either side. Tunneling plays a crucial role in atomic stability by allowing electrons to exist in configurations that would be impossible in classical physics. The electron in a hydrogen atom's ground state exists in a spherically symmetric orbital. That brings it very close to the nucleus. So close that classical electromagnetic forces should cause immediate collision and annihilation. But quantum tunneling allows the electron to maintain this close proximity without actually colliding with the nucleus by continuously tunneling through the potential energy barriers that classical physics would find insurmountable. But tunneling also reveals why atomic collapse doesn't occur through a different mechanism than radiation. Even if electrons could somehow avoid radiating electromagnetic energy, they might still be expected to tunnel directly into the nucleus, where they would be captured by the strong nuclear force. The nucleus represents a deep potential energy, while that it should attract electrons through quantum mechanical tunneling effects. Why doesn't this nuclear capture happen? The answer involves a delicate balance between tunneling probability and energy conservation. While electrons can tunnel into the nucleus, they would need to tunnel into a proton to form a neutron, a process that requires precise energy matching and is suppressed by the weak nuclear force's extremely slow interaction rate. The nuclear tunneling that would destroy atoms is possible, but so improbable that it occurs on timescales much longer than the age of the universe. Quantum mechanics allows atomic collapse through nuclear tunneling, but makes it so unlikely that atoms remain stable for cosmological timescales. Tunneling also explains how nuclear fusion occurs in stars, including our Sun. The protons in stellar cores don't have enough kinetic energy to overcome the electromagnetic repulsion between their positive charges. Classical physics predicts that nuclear fusion should be impossible at the temperatures found in stellar cores. The protons can tunnel through the electromagnetic barriers that classically confine them, allowing nuclear fusion to occur at rates sufficient to power stars for billions of years. This stellar tunneling reveals the cosmic importance of quantum mechanical effects. Without quantum tunneling, stars could not sustain nuclear fusion, and the universe would be cold, dark, and lifeless. The same quantum principles that prevent electrons from radiating energy in atoms also enable the nuclear reactions that power stellar evolution, element formation, and ultimately, the energy sources that sustain all life on Earth. Tunneling effects extend far beyond individual atoms to enable complex molecular processes essential for life. DNA replication depends on quantum tunneling of protons between base pairs, allowing the double helix to unzip and copy itself with the precision necessary for heredity. Enzyme catalysis relies on tunneling effects that allow chemical reactions to occur at body temperature that would otherwise require much higher activation energies. Photosynthesis uses tunneling to transfer electrons across cellular membranes with efficiency approaching theoretical limits. The technological applications of quantum tunneling have revolutionized modern electronics. Tunnel diodes use controlled tunneling through semiconductor barriers to create electronic devices with unique properties. Scanning, tunneling microscopes can image individual atoms by measuring the tunneling current between a sharp probe and a surface. The current depends sensitively on the distance between probe and surface, allowing atomic-scale resolution. Flash memory devices store information by trapping electrons through tunneling into isolated semiconductor regions, where they remain stable for years. But tunneling also creates fundamental limits for electronic miniaturization. As semiconductor devices become smaller, tunneling effects that were once negligible become dominant. Electrons can tunnel through increasingly thin insulating layers, creating unwanted current leakage that limits device performance. The continued miniaturization of electronics must contend with quantum tunneling effects that become more pronounced at nanometer scales. Perhaps the most mind-bending aspect of quantum tunneling is its relationship to time and causality. When a particle tunnels through a barrier, how long does the tunneling process take? Experiments suggest that tunneling might occur instantaneously, faster than light could travel across the barrier width. This doesn't violate special relativity because no information or energy is transmitted faster than light, but it does suggest that tunneling involves temporal behavior that has no analog in classical physics. Some interpretations of quantum mechanics suggest that tunneling particles take all possible paths simultaneously, including paths that involve traveling backward in time or moving faster than light. The particle explores every possible trajectory through the barrier and then chooses one path when the tunneling process is completed. This interpretation implies that quantum particles have access to space-time regions and causal relationships that are forbidden to classical objects. The tunneling that protects atoms from classical collapse while enabling the complex quantum processes necessary for chemistry and life represents one of the most counterintuitive predictions of quantum mechanics. Particles can move through barriers they cannot classically penetrate. Reactions can occur without sufficient classical energy, and information can be transferred through mechanisms that seem to violate space and time. These impossible processes are not just theoretical curiosities, but practical realities that govern every aspect of atomic and molecular behavior. The universe operates according to quantum mechanical principles that allow particles to tunnel through barriers, enabling the complex structures and processes that classical physics would prohibit. We exist because quantum tunneling makes possible a rich variety of atomic and molecular configurations that would be forbidden in a purely classical universe. The quantum world reveals that reality is far more flexible and mysterious than classical intuition suggests, allowing particles to achieve the impossible through mechanisms that continue to challenge our understanding of space, time, and causality. Chapter 7. Virtual reality, the vacuum of space is not empty. This seemingly simple statement represents one of the most profound discoveries in modern physics and holds the key to understanding why electrons do and radiate energy away in atoms. What we call empty space is actually seething with virtual particles, ghostly entities that pop in and out of existence so rapidly that they cannot be directly observed, yet their effects can be measured with extraordinary precision in sophisticated experiments. These virtual particles are not science fiction, but direct consequences of the uncertainty principle applied to energy and time. Just as Heisenberg showed that position and momentum cannot be simultaneously measured with perfect precision, quantum mechanics reveals that energy and time also obey an uncertainty relationship. This means that energy conservation can be violated for brief periods, allowing particle-antiparticle pairs to borrow energy from the vacuum, exist for fleeting moments, and then annihilate back into nothingness. The timescales involved are almost unimaginably brief. A virtual electron-positron pair might exist for only 10 to 21 seconds, a billionth of a billionth of a billionth of a second. During this impossibly short lifetime, the virtual particles cannot travel far or interact strongly with other matter. They exist in a quantum limbo between reality and non-existence, influencing the physical world through their mere potential to exist rather than through classical interactions. But these ephemeral virtual particles have very real effects on atomic structure and electron behavior. The vacuum around an atomic nucleus is filled with virtual photons, particles of light that appear and disappear before they can be detected. These virtual photons create a constantly fluctuating electromagnetic field that slightly alters the energy levels of electrons in atoms. The effect is incredibly small but measurable with modern precision instruments. This vacuum polarization, as physicists call it, provides a subtle but crucial mechanism for atomic stability. The virtual particles surrounding an electron create a kind of quantum cushion that modifies the electromagnetic interactions between the electron and the nucleus. Instead of the clean, simple electromagnetic attraction predicted by classical physics, the electron experiences a slightly modified force that includes quantum corrections from virtual particle interactions. These quantum corrections help explain why classical electromagnetic theory fails to predict atomic collapse. The theory assumes that electrons interact with the nucleus through pure electromagnetic forces in empty space. But space is not empty. It is filled with virtual particles that modify electromagnetic interactions in ways that classical theory cannot account for. The virtual particle sea provides additional mechanisms for energy exchange that can stabilize electron orbitals against classical radiation losses. The reality of virtual particles was dramatically confirmed in 1948 when Willis Lamb measured tiny shifts in the energy levels of hydrogen atoms. These Lamb shifts were exactly what quantum field theory predicted from virtual particle effects. But they had no explanation in classical physics or even in the original formulation of quantum mechanics. The Lamb shift provided the first direct evidence that the vacuum contains physical entities that influence atomic structure. Even more striking confirmation came from the Casimir effect, predicted in 1948 by Hendrik Casimir and first measured in 1997. When two parallel metal plates are placed extremely close together in vacuum, they experience an attractive force that has no classical explanation. This force arises because the virtual particles between the plates are restricted to specific wavelengths that fit between the plates, while the virtual particles outside the plates have no such restrictions. The pressure difference created by this asymmetry in virtual particle density creates a measurable force between the plates. The Casimir effect proves that virtual particles are not just mathematical conveniences, but physical realities that exert forces and carry energy. The vacuum is not a passive backdrop for physical processes, but an active participant that influences the behavior of matter and energy through virtual particle interactions. This quantum vacuum is the stage on which atomic stability plays out, providing mechanisms for energy conservation and electron protection that classical physics never imagined. Virtual particles also explain one of the most mysterious aspects of atomic radiation, why it occurs at all, given that stable atoms don't radiate. When an atom absorbs energy and an electron jumps to a higher energy level, it eventually emits a photon and returns to a lower level. But what triggers this emission? Classical physics suggests that unstable systems should decay continuously, but quantum mechanics shows that atoms in excited states can remain stable indefinitely until something triggers the transition. The answer lies in virtual photon interactions. Even in excited states, electrons are constantly interacting with virtual photons from the quantum vacuum. Occasionally, a virtual photon interaction provides just the right perturbation to trigger a transition to a lower energy level, causing the emission of a real photon. The vacuum itself acts as a catalyst for atomic transitions, providing the random triggers that cause quantum jumps between energy levels. This virtual reality extends beyond individual atoms to encompass all of electromagnetism. What we call electromagnetic forces are actually mediated by virtual photons exchanged between charged particles. When two electrons repel each other, they're exchanging virtual photons that carry momentum and energy between them. The electromagnetic field itself is composed of virtual photons that pop in and out of existence, creating the forces and interactions that govern atomic structure. The concept of virtual particles reveals that the classical distinction between real and unreal breaks down at quantum scales. Virtual particles cannot be directly observed or isolated, yet they produce measurable effects on atomic energy levels, create forces between objects in vacuum, and mediate all electromagnetic interactions. They exist in a quantum superposition between existence and non-existence, influencing the physical world through their quantum mechanical properties rather than through classical material presence. This virtual reality also provides insight into why quantum mechanics successfully predicts atomic stability, while classical physics predicts collapse. Classical physics treats electromagnetic interactions as occurring in empty space with perfect mathematical precision. But quantum field theory recognizes that all interactions occur in a medium of virtual particles that modify the simple classical relationships. The quantum vacuum is not empty, but filled with fluctuating fields and virtual particles that provide additional mechanisms for energy conservation and stability. The virtual particles surrounding electrons in atoms create what physicists call vacuum fluctuations, random changes in electromagnetic fields that occur even in the absence of any real particles. These fluctuations are too rapid and too small to be observed directly. but they alter the effective electromagnetic environment experienced by electrons. The electron doesn't just interact with the nuclear charge through empty space, but through a quantum medium filled with virtual photons and electron-positron pairs. These vacuum fluctuations explain why quantum mechanics is probabilistic rather than deterministic. The virtual particle interactions that influence atomic transitions are fundamentally random, occurring according to quantum mechanical probabilities rather than classical deterministic rules. An electron in an excited state doesn't know when it will emit a photon because the virtual photon interaction that triggers the emission occurs randomly according to vacuum fluctuation statistics. The virtual reality of quantum field theory has practical implications for modern technology. Quantum electronics depends on virtual particle effects in semiconductor devices. Laser technology exploits virtual photon interactions to create coherent light emission. Quantum computing uses virtual particle effects in superconducting circuits to create quantum superposition, states that enable parallel computation. But virtual particles also raise profound questions about the nature of existence and reality. If virtual particles influence the physical world, yet cannot be directly observed, what distinguishes them from real particles? If the vacuum contains unlimited numbers of virtual particles appearing and disappearing continuously, why doesn't this create infinite energy density? And if all electromagnetic interactions are mediated by virtual particles, what does it mean for forces to be real? These questions probe the boundaries between physics and philosophy, challenging our understanding of what exists and what it means for something to be real. The virtual reality that protects electrons from radiating energy away reveals that the quantum universe operates according to principles that transcend classical notions of existence and non-existence. The ghostly virtual particles that fill the vacuum around atomic nuclei represent one of the most mysterious aspects of quantum mechanics, yet they provide crucial mechanisms for atomic stability and electromagnetic interactions. We exist in a universe where the distinction between real and virtual, between something and nothing, becomes meaningless at the quantum scale, where the fundamental processes of matter and energy actually operate. Chapter 8. Measurement Problem. At the heart of quantum mechanics lies a mystery so profound that it has puzzled the greatest physicists for nearly a century: the measurement problem. When no one is looking, electrons exist in quantum superposition states that can include multiple energy levels simultaneously. But the moment someone tries to measure which energy level the electron actually occupies, the superposition collapses and the electron suddenly chooses a definite energy level. This collapse process seems to violate every principle of physics we understand, yet it happens every time any quantum system is observed. The measurement problem is directly connected to atomic stability because it explains not just why electrons don't radiate energy continuously, but why they can exist in stable superposition states for indefinite periods until something disturbs them. Before measurement, an electron in an atom doesn't have a definite energy level. It exists in a quantum superposition that includes components of multiple energy levels with different probability amplitudes. The electron is somehow in all these energy levels at once, a state of affairs that has no analog in classical physics. This superposition state is not just a mathematical convenience or a reflection of incomplete knowledge. According to quantum mechanics, the electron genuinely doesn't have a definite energy before measurement. The superposition represents the electron's actual physical state, not our ignorance about which energy level it really occupies. The electron exists in a quantum limbo where classical concepts like definite energy simply don't apply. But when someone tries to measure the electron's energy level by shining light on the atom and analyzing the scattered photons, for example, something dramatic happens. The smooth, continuous evolution of the quantum superposition suddenly stops, and the electron abruptly chooses one specific energy level. The measurement process transforms the quantum superposition into a definite classical outcome. But the mechanism behind this transformation remains completely mysterious. The measurement problem becomes even more puzzling when you consider what constitutes a measurement. Does the measuring device need to be conscious? Does it need to be macroscopic? Can microscopic quantum systems measure other quantum systems? Or does measurement require some special classical apparatus? Different interpretations of quantum mechanics give radically different answers to these questions, and experiments have so far failed to provide definitive resolution. The Copenhagen interpretation, developed by Niels Bohr and his colleagues in the 1920s, simply accepts the measurement collapse as a fundamental feature of quantum mechanics without trying to explain its mechanism. According to this interpretation, quantum systems evolve according to Schrodinger's equation until they're measured, at which point the wave function collapses according to different mathematical rules. The collapse is postulated as a basic law of nature, like conservation of energy or Newton's laws of motion. But this approach leaves fundamental questions unanswered. Why is the wave function collapse during measurement but not during other types of interactions? What determines which outcome the collapse produces when multiple outcomes are possible? And how does the collapse happen? Does it occur instantly throughout space, gradually over time, or through some other mechanism that we don't understand? The many worlds interpretation, proposed by Hugh Everett in the 1950s, offers a radically different solution to the measurement problem. According to this interpretation, the wave function never actually collapses. Instead, every possible measurement outcome actually occurs, but in different parallel universes that split apart during the measurement process. When you measure an electron's energy level, the universe splits into multiple copies, one for each possible energy level the electron might have. You experience only one outcome because you exist in only one of these parallel universes. This interpretation eliminates wave function collapse, but at the cost of proposing that countless parallel universes are constantly being created every time any quantum measurement occurs anywhere in the cosmos. The interpretation suggests that reality consists of an ever-branching tree of parallel worlds, with conscious observers experiencing only one branch while remaining forever, unable to access information about the other branches. The pilot wave interpretation, originally developed by Louis de Broglie and later elaborated by David Bohm, takes yet another approach to the measurement problem. According to this interpretation, particles always have definite positions and velocities, but they're guided by quantum waves that determine their behavior probabilistically. The apparent randomness of quantum mechanics emerges from our inability to observe the pilot waves that guide particle motion, not from fundamental indeterminacy in nature itself. This interpretation preserves determinism and avoids wave function collapse, but it requires accepting the existence of quantum waves that cannot be directly detected and that seem to violate locality by allowing instantaneous influences across arbitrary distances. The pilot waves provide a mechanism for quantum behavior without requiring superposition states or measurement-induced collapse, but they introduce their own conceptual difficulties. The measurement problem has practical implications that extend far beyond philosophical debates about interpretation. Quantum technologies depend on maintaining superposition states for extended periods while preventing premature collapse through unwanted measurements. Quantum computers must isolate quantum bits from environmental interactions that would cause decoherence and destroy the superposition states necessary for quantum computation. Understanding and controlling the measurement process is crucial for developing quantum technologies that can exploit superposition effects. The problem also reveals fundamental questions about the role of consciousness in physics. Some interpretations suggest that conscious observation plays a special role in wave function collapse, implying that minds have unique physical properties that differ from ordinary matter. Other interpretations deny any special role for consciousness, arguing that any sufficiently complex interaction can trigger collapse regardless of whether conscious observers are involved. Recent experiments have attempted to probe the measurement problem by creating quantum measurement scenarios where quantum systems are used to measure other quantum systems. These experiments explore whether measurement requires classical apparatus or whether purely quantum mechanical measurement is possible. The results suggest that measurement might be a gradual process involving entanglement between the measured system and the measuring apparatus, rather than an instantaneous collapse triggered by conscious observation. The measurement problem also connects to deep questions about the nature of time and causality in quantum mechanics. Wave function collapse appears to occur instantaneously, potentially violating special relativity if the collapse affects entangled particles at distant locations. But if collapse is gradual, what determines its timescale and mechanism? And if collapse never occurs, as suggested by many worlds' interpretation, how do definite measurement outcomes emerge from quantum superpositions? These questions probe the boundaries of what physics can tell us about reality. The measurement problem reveals that quantum mechanics, despite its extraordinary predictive success, may not provide a complete description of how the universe actually works. The theory tells us how to calculate probabilities for measurement outcomes, but it doesn't explain how or why these outcomes are selected from the range of quantum possibilities. The stability of atoms depends on electrons existing in quantum superposition states that don't undergo classical measurement collapse under normal circumstances. The electron in the ground state of a hydrogen atom exists in a superposition that includes interactions with virtual particles, responses to external fields, and correlations with other quantum systems. This superposition remains stable because the electron's environment doesn't provide the kind of strong measurement interaction that would force collapse to a definite classical state. But when atoms interact with intense electromagnetic fields, absorb or emit photons, or participate in chemical reactions, measurement-like processes can occur that force electrons into definite energy levels. Understanding how to control these measurement interactions is crucial for technologies ranging from atomic spectroscopy to quantum information processing. The measurement problem that protects atomic stability while enabling quantum technologies represents one of the deepest unsolved mysteries in physics. We know that quantum superposition prevents electrons from radiating energy continuously, but we don't understand how superposition states maintain their coherence, or what triggers their collapse into definite classical outcomes. This mystery lies at the heart of the quantum mechanical description of reality, challenging our understanding of existence, measurement, consciousness, and the relationship between quantum possibilities and classical actualities. The measurement problem reveals that the quantum solution to atomic stability is not just different from classical physics. It's based on principles that may forever remain beyond complete human comprehension.